All right, great. In this section, we said we are going to talk about assessing model accuracy, right? So previously we were talking about finding an f that sort of gives the relationship between your x and your y. If this is income, we want to find an f that will relate our x's like age, school, seniority, and stuff like that. How do we estimate income using our x's? And we do that by using this function f, whatever function f it's going to be, depending on what model we use. If we use regression or whatever it is, right? Cool. But how do we, because we have so many different statistical models, right? How do you know which model is the best one? That is the discussion in this section. How do we assess that our model is working properly, right? So it is important to test which model works best for a set of data, because not all statistical models or methods will perform well on a set of data. Selecting the best model can be quite challenging, and one of the most difficult parts of performing statistical learning in practice, right? So selecting the best model would be a bit difficult, but there are techniques that we can use, and we are going to discuss the high level of them. Each and every chapter here, we are going to discuss methods of selecting that particular model. But here, since this chapter, the first chapter is just introduction into everything, we're going to just discuss the high level of it. The first part we are going to discuss is measuring quality of fit. Quality of fit. That's what we're going to discuss in this video. And this really applies. We're going to use regression as the main example. So evaluating performance we ask them their age, we measure their height, the school they went to, seniority, we put it in a table like this, right? And then we know how much we're giving them. We know how much we're giving them, the income. So we do that for many people. We do that for many people, right? And when we are training our model, because this is going to be training data, because we have everything, we're trying to predict income for people who we don't know, who's going to walk into our company. But first we have to use this training data, right? We have to use this training data to come up with our F, and to come up with this F here. When we are doing that, when we are using training data, we are going to, let me see, where is my tool? Yeah, I think it's this one here, because I want to remove this. Just going to delete this, because what happens is, okay, we understand that is our training data, right? So what is going to happen is, when we are training, we are going to come up with predictions for income. We will get the person's age, height, school, seniority, and then we predict their income. And we compare the two. How far am I from the correct one? How far am I from the correct one? We do that for the same person when we're training, trying to figure out our F. Put our height, age, height, school, seniority, right, into our X. Into our X, we put all those. We try to estimate. We use our estimate for F, and then we come up with another income here for the second person, and we compare how far is that second person's income from the true income that we measure, that we know we are paying them, right? So this is this part here. We need a way to measure how well our predictions actually match what we have observed. So this is what we observed, the observed income, right? Observed income. So we're going to call that Y, and this is the predicted income for each person, and we'll call it Y with a hat like that, because that is what we're predicting, like in this equation here. Cool. So What we're basically saying is we need to quantify the extent to which the predicted value for any given observation is close to the response value, or the thing that we have observed. For this observation, for person number 1, we need to quantify, we predicted this income. How far is it from the one that we are actually paying them? And we quantify that difference, right? In regression, most commonly used measure is called the mean squared error. Mean squared error. And it's abbreviated as we are going to use MSE so much in this chapter, so it's going to be MSE. It is given by 1 over n summation of, I'll explain what this means. It's not very confusing. Squared. Cool. So basically what we're doing here is, this is my yi for this person. I can call it y1 because it's for the first person. And this is the actual income, y1. So this is y1 with a hat, because that's what we predicted. y2 with a hat, that's what we predicted. And y2 for the actual one. So what is the difference between the two? It's definitely y1 minus y1. So we can say the actual y minus the predicted. The actual y2 minus the predicted y2, right? And we can add these differences. We can add, this is the difference from the first person. This is the difference from the second person. Let's add them up. And then we get the average. How many people are there? We divide by 2. That's basically what we're doing here. We are adding the difference between the actual and the predicted, because you know that this is this part here, this fxi, this is basically yi with a hat. So adding the difference between the actual and the predicted for each observation, this I means each observation from observation number 1 to observation n, we add them up and then we just divide by how many observations we have, the n. Here we had 2 observations, so our n was equal to 2. That's pretty much what this is saying. That's how we get how far we are from our predicted values. Right? So what this means is our MSE will be small, or MSE will be small if these predicted values, the yi hats, are very close to the actual. Because if these two are are close to each other, the actual and the predicted, if they are close to each other, then means when you subtract them, we get a very, very small number. So we're adding a very small number and then divided by n. So our MSE will be very small. But if there's a large difference between our predicted and our predicted here and our actual, then this difference, yi minus yi hat, is going to be large. So it means our MSE is going to be large, right? So the one that we have calculated here, you see, where did we get our MSE from? We got it from using our data here. But what type of data is this? This is our training data, right? It is our training data because we know the income and stuff. So we're calculating using things that we already know, which is our training data. So to be very, very precise, the one that we would have calculated here is called the training MSE. It's called the training MSE. Generally, what we are concerned about when we are building predictive models like this, we are not really concerned about the training MSE. Why? Because, like here in this case, we already know the person's income. So there's no need for us to even be concerned about how well we are predicting the person's income, because we already know what it is. What we are concerned about is the test MSE. The test MSE. The test MSE is that error that will come about when someone new walks into our company and we predict their income to be whatever level that we predict it to be. We want to make sure that our model is accurate enough to predict the correct income for the person, because there's no way for us to compare with the actual income. We don't know what the actual income is. We don't know what the actual income is. This person is new to the company, so we are predicting their income. We don't have anything to compare with, right? So we want to make sure when we train our model, we want to train our model in such a way that we can at least get a glimpse of this test MSc. Is it going to perform well on unseen data? Because if we just focus on training MSc, we might make an error, because it might happily predict the correct income for the guys that we already know. But for someone we have never seen before, it might actually give us wrong results, right? Wrong results. It might give us low income or high income. So we want to make sure when we're training it, we keep in mind that test MSc is one that is very important, because that is what we want to predict. We want to predict people we do not know about, right? So this can be done, calculating this test MSc. It can be done. Let's say we have our observations like this. We have our observations. What we can do is we can say, let's keep this section here as the test data, right? As the test data. We split out a section of our observations. We'll be like, maybe from, let's say we have 1 to 10,000 observations, right? These are the observations that we have in our training data. We might say, okay, we'll train our model with 1 to 8,000. And then from 8,001 to 10,000, we're going to keep this separate as our test data. We're going to pretend these are new people. And we will train our data here, figure out the F, and then we'll see how accurately it's going to predict for these people as a testing, not for training. That's what we'll do. Some people will actually keep also a validation set, but I think in this course we're just going to split our data into the training data that does all the hard work of figuring out what the F is, and then the test data that allows us to calculate this test MSc to see, for people you have never seen before, how well are you doing? If it's performing well, badly here, we know that we haven't trained well. We'll go back to train it. We're not really concerned about the training error. We want to make sure that this is where it's at, the test for the test data, the test error, right? So if we cannot split our data like this, if there's no test observations, there's no guarantee that the model with the low training MSc will equal the model with the lowest test MSc. So many learning models estimate many models, they estimate using this training data. So we need a way to just incorporate a way to get this test MSc, right? So just to put this into perspective, let's see what we mean here. So let's say we have generated. Let me see how much space we have here. I think we have enough space. Cool. Let's say we have generated observations that we already know. We know the accurate data. We know the accurate incomes. We know everything. This is stuff we've just generated in the lab, right? We've just generated this for fun to prove a point, right? So let's plot that data. Let's plot that data and see what the results will be, right? Let's say our data comes out to be something like this. When we're plotting it, we plot it like that. Let's say it comes out like that, right? And since we have created this just for fun, this black line is the actual trend. That is the actual trend, because we created this data, so we know what the actual trend is. So this is the actual trend. Cool. Now let's try to fit a couple of models. One can say, I'm going to fit a straight line through this. I'm going to regress a straight line like that. Cool. Persons, they fitted a straight line through the data. Yeah, that is the green one there. Another person might say, when I fit linear regression, I'm going to come up with a line that is like this, the blue line. Cool, right? And then another person as well. Let me see if I can get a different color. another person might fit a line that, I hope you can see this, that follows each point wherever it is. It follows the points exactly like that. Follows the points exactly like that. So we have three models. Right? We have the straight line model, which is green. So let me try, right? So the three models that we have this line that is a straight linear line. Cool. And then we have the blue model that is a bit like this. I don't know, it's using the wrong color. Yeah, this. So let me quickly delete that. Okay, so and we have a blue line like this, right? This is it's a bit non-linear. We can call it non-linear. And then we have the other guy here. The other guy has this very wiggly line. We just call it wiggly. We have a wiggly curve like that. Cool. So those are the models that we have. What we want to discuss, right? We want to discuss the difference between training MSE and test MSE. Which one is the best model to choose here? That's what we want to discuss here. Cool. So this panel shows automatically generated observations with true F given by the black curve. The others represent three possible estimates of F obtained using methods of increasing flexibility. As you can see, the wiggly one is much more flexible. The green, the straight line, not very flexible. Non-linear is more flexible than the straight line, but then wiggly one is more flexible than the non-linear one. So we just increased flexibility. So this line here, this green line is the linear regression fit, which is relatively inflexible. Then we are followed by the blue and the wiggly line. Let's say we created them using flexible methods like the spline, straight line spline, like this, the smoothing splines. We'll talk about these methods later. Let's just try to get a sense of what we're trying to get here, the difference between training and test MSE. So as the level of flexibility increases, the curves fit the observed data more closely. As you can see, the wiggly one is now following the data way closely. It's like more closely, way more than the straight line. The straight line just went cha without even considering where everything is. But the wiggly line, it's more flexible, so it's following the data more closely. Now let's plot the errors. Let's try plot the errors here. Let's create another graph on this side. Cool. So I'm going to put this dashed line here. I'll explain what it is. Cool. Let me get another color. Let me see if I can get another color here. I can just use, but I would want to use some different colors. So let's say if you can see this as brown. So this brown line, I'm going to draw it like this, and I'll explain what I'm doing there. Cool. So we have that brown line. Let me get something that's like pink maybe, or purple. Purple is much better. Ignore that. Purple is much better. So cool. And I'm going to have a purple line that goes like that. Perfect. Right? So let's explain what is going on here. The right panel, this brown curve shows the average training error or training MSE. So this shows the training MSE. I'll explain why it comes out like that. That is the training MSE as a function of flexibility. So yeah, it's increasing flexibility. So as flexibility increases, this is what happens to the training error. I think it sort of makes sense. Let's reason out. Basically, training MSE is saying how far are my predictions from my actual data, where my actual data is, right? So what is happening here is with the green line, let's look at the green line. With this green, this is what we are predicting. We are predicting that these are the, let's say, the incomes. They lie on a straight line like this. But can you see there's large difference between the actual data points and the predicted by this, and the predicted, let's say, incomes by this green line? For every, I would say for every point, there is a difference. And that is the error. That is the error for every single point. There is an error. So our green line here will be up there. The training error for the green line is somewhere up there. Low flexibility, high error rate. So that's something I didn't write. So here it is just a measure of MSE. So on the vertical axis, it's MSE, right? So what this basically means is for something that is not flexible, that's like this green line, the straight line, we have a high MSE, low flexibility, high MSE. Let's look at the blue line. The blue line is very close to the pattern that is there in the actual data itself, right? So what that results in, it results in some error. Of course, it's going to result in some error because it's going to result in some training error. Why? Because if you look at the blue line, it is not following these points. There are some gaps between the points themselves and the blue line. So there is some level of error. It is more flexible, so it's more flexible. It's more flexible than this green one, but it has a lower error. So the blue line, let's just say, the blue line, let's just say its training error is there. That is where the blue line training error is. Now let's talk about our wiggly line. The wiggly line, as you can see, the wiggly line is following each point accurately, like where each point is, it is there. So which means there is no gap between the points and the wiggly line. So that is why it is very, very low MSE. It has low MSE because it's following each point accurately. Very flexible, very low MSE. So that is the training MSE. Someone might be happy and say, someone might say, I'm going to take the wiggly line because it has the lowest training MSE. But like I explained before, we do not want to focus on training MSE. We want to focus on test MSE. So let's see how we can do that. Oh yeah, so another point that I didn't raise here. For all statistical methods, training MSE decreases monotonically or continuously decreases as flexibility increases. Right? As you can see, flexibility is increasing, our training MSE keeps decreasing. So now, we are going to now look at test MSE. I said previously that test MSE is difficult to get because sometimes we don't have the test data. We do not know the incomes, like the incomes of people that are walking into the business and stuff like that. But here, this is simulated data. So we know our actual line. Our actual line is the black one. So when we are doing our test MSE, we are going to see how far is this line from our black line, because the black line is the actual one. We created this data out of thin air, but by creating it, we know what we're aiming for. We know we are aiming for the black line. So cool. How far the model is from the black line gives us our test MSE. Perfect. So now, let's see how that happens. What happens is, for the green line, for the green model, that is just a straight linear regression model, it will have a high test MSE. Oh, that's something I didn't mention. The purple line, this one here, is the one that shows us our test MSE. Let's dig deep into what it's saying. For this green line, the straight linear model line, this linear model line, you can see that there are gaps between the black, the actual, and the predicted model. There are gaps there, right? Since there are gaps, we're of course going to have a high test MSE. Cool. Let's go on to the blue line. The blue line is very, very close to the actual. It's close to the actual. So what that means is it will have a very low test MSE. It will have a low test MSE because it is sort of like following the actual trend in the data itself. It's following the trend in the data itself. But our weekly one, oh my goodness, the weekly one, although it had a low training MSE, look how it is differing from the black one, the actual one. It is differing by so many values for look how it's wiggling past the black, and then after it's like going all over the show. So it will have a high test MSE. It's going to have a high test MSE. So this blue one, it reduces the test MSE because, as seen, it appears to estimate the actual F, the black line, the best in the left hand panel here. It's the one that is estimating the black line better than all of them. So it has the lowest test MSE. Let's talk about this dashed line. This dashed line, if you remember in my previous video, I said there are two types of errors, reducible and irreducible. This is the irreducible error, this dashed line. It's error that we cannot get rid of, right? That's the irreducible error. And as you can see, the irreducible error is the lowest achievable test MSE. Let's say we are testing perfectly. We have a test MSE that is equal to, it's not going to be equal to 0. If our test, if for this black line here, this black line is the true one, right? It will have a test MSE that is equal to the irreducible, or the error we can never reduce. That's what it basically means. So it will be the lowest test MSE. Perfect. I think that makes sense, right? Training MSE, as we can see, it decreases monotonically, and the test MSE, it always has a U shape. This one will always have a U shape, regardless of what of the data set or the method that we're using. If we're using regression, linear regression, nonlinear regression, polynomial regression, if we're using KNN, we're going to discuss those methods later. No matter what it is, these are the shapes of the training MSE and the test MSE. When model yields a small training error, like this one here, the wiggly line, but a large test MSE, we get into a phenomenon called overfitting. We get into a phenomenon called overfitting. And what overfitting basically says is we are following the data points way too closely. We are really not getting the overall trend in the data. We are just following the data points. Like you see this wiggly model here. What was it? It was just following the points. It wasn't telling us how overall how is this data related. It wasn't telling us that. It was just following. It was just following wherever there is the point. It was just going there. So we were overfitting our model. The one that gives us the overall trend is the black line, right? There's no overfitting there. But this one here that follows all the points, it's overfitting because it is a low training MSE. Yeah, you're following the points, so you're training well. Would say you're training well, low training MSE. But when we apply test MSE, when we look for the test MSE, very high test MSE. So overfitting is when training MSE is high, training MSE is low, and then the test MSE on data that we have never seen, we now see so many big errors. Because what happens is, because of this wiggly line, now imagine someone walks into the company and their point is there. This wiggly line is not going to tell us how much we should pay them because it's following all the points following the points too closely. It's difficult to use this to predict what the person is supposed to get. It doesn't give us the overall picture. That's what we are concerned about when we do predictive modeling, right? So let's see. I'm just looking at my notes here to see where I am. So in practice, estimating training MSC, this training MSC is relatively easier than test MSC because sometimes we do not have this test or data to do the testing, right? But there are variety there are many ways, there are variety of approaches that can be used to estimate this test MSC and then selecting the model that is the minimum one, right? Methods like, we're going to discuss this later, methods like cross validation, they are very, very important for us to estimate this test MSC, because now when we've estimated the test MSC, we'll be like, the green one, we're not going to take the green model. We're not going to take this wiggly model. We're going to take the blue model because that is the one that is the lowest test MSC. We don't use the training to decide that. We use the test MSC. And if we do not have the test observations, we can use approaches like cross validation. We're going to discuss them later to estimate this test MSC and then select the best model. This was a relatively long video, but it introduced things that are very, very fundamental to statistical models. We're going to get into the next video is going to talk about something that is also very fundamental called the bias variance trade-off. So stay tuned for that video.